It's Crystal here, and I'm here to make another video for you about about a nonparametric test. And this nonparametric test that we're going to talk about is Fisher's exact test, which is a hypothesis test for association between two categorical values. It's most commonly applied to a 2x2 contingency table when sample sizes are small or expected cell counts are low. It computes the exact p-value using the hypergeometric distribution rather than relying on the chi-square approximation. It evaluates whether the row variable and the common table and a contingency table are independent. So, in Fisher's exact test, the null hypothesis states that two variables are independent, and the alternate hypothesis states that two variables are not independent. So what we're going to do is we're going to go over a sample code of a Fisher's exact test and R. So we're going to create the contingency table 2x2. So table becomes matrix, which is a vector between 4, 9, 8, 4. So the number of rows is 2, and by row is true. And then the column names for table is Democratic, is a vector with Democrat and Republican, and the row names of table is a vector being male and female. And so we're going to print the table. So you can see the table here. So you've got your matrix. So you've got 2 rows and 2 columns. The 2 columns are Democrat and Republican, and the 2 rows are male and female. So now we're going to perform the Fisher's exact test. So Fisher result becomes Fisher.test brackets table, and now we're going to look at the Fisher result. So the Fisher result is the data is table, the p-value is 0.1152, the p-value is greater than the significance level of 0.05, so that means you're going to fail to reject the null hypothesis, so that means that the data in the table are independent. So the alternative hypothesis is true odds ratio is not equal to 1, but we're not going to go with the true odds ratio. We're going to go with the alternate. We're not going to go with the alternative ratio. We're going to go with the null hypothesis. So the 95% confidence level is 0.029 to 1.539, and then the sample estimates are the odds ratio and 0.237. So that's the test that we have performed. And then so now what we're going to do is we're going to plot the results. So we're going to compute the expected counts under independence. So expected becomes outer brackets sum rows brackets table common call sums brackets table over divided by sum table. And then we're going to set up the plotted area. So PAR brackets MF row equals a vector of 1 and 2. And then we're going to set up the observed counts. So bar plot brackets table, comma, beside equals true, comma, column is a vector, color is a vector of steel blue and tomato. Main is the title, which is called observed counts. Frequency is the Y lab, and Y lab is the label on your Y axis. Legend equals true. So we've got expected counts, bar plot, brackets expected, comma, beside equals true, color equals a vector of steel blue and tomato, main is the title, being expected counts independence, Y-lab is your label on your y-axis, is expected frequency, and legend equals true. And then you got PAR brackets MF row equals a vector of 1 and 1. So we run it, and this is the diagram that we come up with. You have two charts, one being the observed counts and one being the expected counts. And then so you can see by looking at the two charts, the observed counts is different from the expected counts. And so since the observed counts are different from the expected counts, and the p-value is greater than 0.05, then that means you're going to go with the null hypothesis, which means that the counts are independent. So that concludes this video. The next video is going to be another nonparametric test. So I hope that you decide to watch it, and I hope that you got something out of this video. Thank you for watching.